Hello everyone, it's Benny, and welcome back to the Ultimate Guide to Redstone. In this video, we're going to be talking about how to do addition with Redstone. So, first off, addition is a mathematical operation. It's the first mathematical operation we're going to talk about in the mathematical circuits portion of the series, because addition is the base of all mathematical operations. So, needless to say, it's really important. So, our first challenge we have to overcome if we're going to do addition. What numbering system do we use? Because, if you recall, we have two ways of representing numbers. We have binary, which we already discussed the advantages of, so I'm not going to reiterate them. And we have unary. And why not? I will reiterate some of them. Okay, so unary requires lots of wires to represent numbers, but it gives you a lot more control over the numbers. Binary lets you represent lots of numbers with very few wires, but it doesn't let you do much other than just represent them. So, which numbering system should we use? I'll save you some headache of figuring out which numbering system will be better. I'm going to just tell you that binary addition machines are much simpler than unary addition machines, for the most part. So, we're going to be focusing on creating a binary adder. Because, well, quite frankly, I think it's a lot nicer system than unary. It's a lot easier to represent lots of numbers, and if you need the extra definition, I guess you could say, the extra control, you can just plug it into a decoder. So, we're going to be working with binary numbers. Now, that's our first challenge overcome. So, how on earth do we even approach the idea of doing addition with Redstone? Well, I think a good place to start is just solving a binary math equation by hand. Because, if you think about it, we're trying to build a device that does this for us. It makes sense that we understand the process ourselves. So, here I have a nice binary math equation set up. I'm adding 0, 0, 1, 1, which is 3, plus 0, 1, 0, 1, which is 5. And the result of this should get me 8, but we're going to solve it in binary, just to clarify the process. Now, you might think there's some really special way of doing binary addition. As it turns out, you do it the exact same way you do addition in decimal. So to demonstrate, if you remember from grade school math, if you had to add two numbers which had a lot of digits, what you do is you start in the ones place, and you'd add those. So, in the ones place here, I'm doing 1 plus 1. Now that's 2, which is 1, 0. But, as you can see, I only have one digit place here. So, for the next one, just like in grade school math, I carry that over to the next digit place. Now, I'm adding 1 plus 1 plus 0, and that extra 1 is coming from the carry. So, in order to solve this, I do the exact same thing. 1 plus 1 plus 0, well, that's 1, 0. And again, we come across that same issue. We have to carry. So I'll carry that over. Now I add 1 from the carry, plus 0, plus 1. Again, 0 and 1 from the carry, which, turns off, but oh well. And now, we carry that over. Now 1 plus 0 is 1. So as a result of adding 0, 0, 1, 1 plus 0, 1, 0, 1, we get 1, 0, 0, 0, which is 8. So 3 plus 5 is 8, which is correct. So, it makes sense that in order to do binary addition, we're just going to build a Redstone device that does this exact same process. So, let's take a look at how we're going to build a Redstone device that does this, because it's a pretty straightforward process, so it shouldn't be that hard. Now, the way I'm going to handle it is I'm just going to take it bit by bit, because if you think about it, we're just doing the exact same process for every single digit place. Here I added 1 and 1, and then I got a result and a carry. Here I added the carry and A and B, and I got a result and the carry. Here I added carry A and B, got a result and carry, and so forth and so on. It's the exact same process for every single place. So why would we build a device that explicitly handled 4 bits when we could just build one generic device that handles a bit and just use that to create as many bits as we want? So that's exactly what I'm going to do. And I'm going to start by just laying out how we're going to do this. So, one moment. Okay, so this right here, this is a model of how our device is going to work. So I have input 1A, input 1B. Here's my output for my ones place, and output for my twos place, or my carry. So here's how the device is going to work. Right now I'm adding 0 plus 0, so that should give me 0. If I add 1 plus 0, that should give me 1. Okay, makes sense. If I add 0 plus 1, that should give me 1. Makes sense. If I add 1 plus 1, that's 2, so that should give me 1, 0. Okay. So, if you think about this, this might seem not exactly obvious at first, but I think the easiest way to implement this is just to plug each of these inputs into a logic gate, and each logic gate is going to compute the ones place and the carry respectively. So I'm going to have one logic gate that computes this, and one logic gate that computes the carry, and I'm just going to plug the same two wires into those logic gates, and that'll do it for us. So first off, this wire, the ones place. What does that? Well, first off, we illustrated if we have 0 and 0, we want our output to be 0. Okay. If we have 1 and 0, we want our output to be 1. If we have 0 and 1, we want our output to be 1 as well. And if we add 1 and 1, well, this is where I have to be careful, because 1 plus 1 is 1, 0. And in this place, that's a 0. So, if I place wire here, this is a complete truth table of the logic gate that will get us this bit right here. This one right here. So, what logic gate is this? If you think about it for a bit, you'll realize that this is an Xor gate. Because, if you think about it, it is just like an OR gate, except the output is 0. It behaves just like an Xor gate. This is a table for an Xor gate. So I'll just put a sign. This bit we get with an Xor gate. Now, what about this bit? Okay, so I'll just get rid of all this. So we have a nice clean working space. So, yeah. Now, for this one, if we have 0, 0, our output should be 0. Okay, good. 1, 0, output should be 0. So, 1, 0 gives us 0. 0, 1 gives us 0. And now, 1 plus 1, that's the only thing that gives us 2. So that's the only thing that will give us a 1. Now, if you think about this for a bit, you'll realize this is this same truth table for an AND gate. If A and B, then an output. Nothing else gives us an output. So for this bit, we're going to get that with an AND gate. And if you look, we have the process for building an adder completely laid out for us. So, I'm just going to erase this, and let's just go straight into building this thing. Okay, to start, I'm going to build the Xor gate. So, here's input A, here's input B, and here's the Xor gate. So, it's pretty simple, exact same Xor gate we built earlier in the series. So it all starts with the OR gate right here. A or B. Good. And then, in order to make this into an Xor gate, we have to make it 0 when both inputs are on. So I'm going to build an AND gate based on these torches to test if both inputs are on. And if both inputs are on, I'm going to power this, which will stop us from getting an output. And that creates an Xor gate. Okay, good. We now have an Xor gate. The first bit is complete. Now, for the second bit, we need an AND gate. Now, rather than just build a completely separate AND gate, I'm going to take advantage of the fact that an AND gate is part of the Xor gate, and I'm just going to use this. Now, getting the output as is a little tricky, so I'm going to move this. I'm going to place a block here. Since this is a dot of redstone, this block will still receive power, so I can still do like this. And right here can be the output of my AND gate. So if I just shuffle these around a bit to make it a little bit obvious, we now have the adder that I was talking about. 0, 0, okay, that's 0, 0, good. 1 plus 0, okay, that's 1, good. 1 plus 0, that's 1, good. 1 plus 1, 1, 0. We've just built an adder. But this actually isn't an adder yet. This is actually a half adder. And here's why. If we go back to our equation for a second, you remember 1 plus 1, that is indeed 1, 0. But what did we do with the 1? We carried it over. And now we're adding 3 terms. So, in order to make this half adder into a full adder, what we have to do is we have to have some way of taking in that carry. So, how do we take in a carry? Well, first off, I'm going to take advantage of the fact that no matter what, nothing is going to change this bit right here. Because even with 3 bits, even with 3 ones, that's still only going to add up to 3. We can never carry over to a next bit. So that's the good news. We still only need this and this. The bad news is we still need to change this bit in some cases, and in some cases we have an uppercase where this will turn on. So, the way I'm going to solve this huge conundrum is just with another half adder. And here's how. First off, if I plug this device right here, I'm actually going to move the wire over this way. And do I actually want to do that? Yes, I do. Okay. If I plug this into another half adder, then this lets us essentially add another bit to our ones place. Because you remember, the way we add to the ones place is with Xor. So this is the first half of completing our full adder. So now we have a way of adding to the ones place, because adding to ones place, well, that's just an Xor Gate. So if I move this so that, yeah, interesting wiring to actually get a wire that I can plug in, but okay. If I add this, you notice that's adding to the ones place properly. So yeah. Now the only thing left is getting the extra case where it can be AND, because right now, if I do this and this, that should give us an AND. Well, if you notice, this Xor Gate now has its AND turned on. So, if I just get power from that last AND, that gets our carry wire correct. So, all we need to make a half adder into a full adder is another half adder, which makes logical sense if you really think about it. So, yeah. Now we've completed a device which theoretically should be able to perform this addition we talked about earlier. So I'm just gonna I'm just gonna keep it like this for a second. I'm gonna use World Edit to make 4 bits of this for us. So, if I do position 1, and move over, and to make this a bit easier, I'm going to do like this. And the reason we do like this is because this way our carry wires will connect automatically, and that means we won't have to do any interesting wiring of the carries later on. So, that's just for convenience, nothing to do with the math. Position 2. Okay. Now I'm going to stack and make 3 more of these, and this should give us our fabled binary adder. So, this is our ones place, and this, and this is input B. I said that backwards, didn't I? Okay. This, and this is input A, and this, and this is input B. Okay, fair enough. And of course, this is our carry in, if for some reason we needed to carry in. And this is the carry out of the final adder. So, this just lets us know if we have an extra bit. So let's pump in the numbers we had before. So for input A, we had 3, so there's 3. And for input 2, we had 5, so that's 5. Now this should give us 8. And it's magic, we have 8. This is doing the exact same logic I've been talking about the whole video. It's doing the exact same math equation you've been learning about all your life. It's pretty simple, and it's pretty amazing. And that's the basics of binary addition. Okay, so that's pretty much everything you'll ever need to know about how binary addition works. But there's still one more thing that you might be concerned about when you're doing binary addition. And that is speed. Because, well, like I said at the beginning of the video, binary addition is the basis of all mathematical operations in Redstone. So if you have all your math done based on slow addition, inevitably your math device is going to be slow. Okay, so that's pretty much all you need to know about how binary addition works. But there's still one really major concern when dealing with binary addition, and that is speed. Because, as I said earlier in this video, binary addition is the basis of all mathematical operations. So if your binary addition is slow, then inevitably all your mathematical circuitry will be slow. So it's kind of important to have a fast binary adder. So let's just test this and see how fast this is. That's all I set up right here. This should, in theory, trigger the slowest possible solution that the binary adder can get. So let's test it. If they're the same, if our adder is 8 ticks, then these pistons should extend at the same time. The reason it's 8 ticks instead of 9 ticks is because it takes 1 tick for the signal I'm testing to reach the output due to this repeater. So if we subtract that, it should be 8 ticks from addition. So if I flip this, we have an 8-tick binary adder. For 4 bits, that's really not that good. So how can we make this faster? Well, let's look at our individual adder cell, and let's see what's making it so slow. First, our signal goes into a 3-tick Xor Gate. Then that signal goes into another 3-tick Xor Gate. So that's 6 ticks just for the first bit. That's really not that good. That's pretty slow, all things considered. 6 ticks for just 1 bit. And then you have to get all the other bits. That's not even including the carryover to those, so yeah. One really big way we can improve on this is somehow decrease the delay of these Xor gates, because 3 ticks, pretty slow. So, let's ask a question then. Can we make a faster Xor gate? Well, at least not very easily without dramatically changing the setup. No, we can't. But there is something else we can do. We can take an XNOR gate and plug it into another XNOR gate. And that will create the exact same thing as a 2 XNOR gate chain. The reason is an XNOR gate going into another XNOR gate does the same thing as an XOR gate. So this means we can replace these with XNOR gates. And the reason that's significant is because XNOR gates can be made 2 ticks. So that'd be 4 ticks instead of 6 ticks. And that will just increase changes as time goes on down the line, right? Right, so let's make an XNOR gate-based adder. Now I've already done it, and the reason I've done it off camera is first off, it's not relevant to the point of the video. The point of the video is how it works, not how to build an XNOR gate-based adder. And second of all, you're going to learn a lot better if you try to build these things on your own than if I go and show you everything. The one thing I will mention, though, is since the output of the XNOR is essentially the inverse of what you want, you have to create a separate AND gate for the second half adder going to the carry. And you'll have to invert the input of this second AND gate. So that's all I'm going to say about how you can implement this. So here we go, same basic setup, and let's just start measuring with the same 8-tick delay we had before. So, if I flip the lever, oh, whoa, what's going on here? We have a 4-tick XNOR gate cell, but it's moving at the exact same speed. What's on earth is going on here? And now all my torches are facing burnout glitch, but that's not the point. We made the cell faster, it's 4 ticks now, we have faster cells. Why is our adder the exact same speed? It doesn't make any logical sense. The reason our adder based on a 4-tick cell is the same speed as an adder based on the 6-tick cell is fundamentally because we're trying to measure how fast these devices are based on the number of ticks. Now, that's not to say measuring devices based on their ticks is a bad way of measuring how fast they are, because if it was a bad system, we wouldn't still be using it. It's a very good way of understanding how fast your Redstone device is. The issue with measuring things in ticks, though, is it doesn't give a complete idea of how your device is performing. Sometimes just the direct speed of how fast your device is isn't the real factor of why your device is a certain speed. So sometimes ticks is a really, really bad way of measuring how fast a device is because it's not giving you a complete picture of why your device is. It might be able to tell you that your device is a certain way, but doesn't tell you why it's that certain way as well. And that sometimes can be really, really important. This being a prime example of that. So, in the next video, we're going to be talking about another way we can measure how fast Redstone devices are. This is the same way they measure how fast real-life electronic devices and real-life algorithms are, because it doesn't just tell you how fast it is, it tells you why it's that fast. And it makes it really easy to see exactly what's causing your device to perform and behave in a certain way. And it's not appropriate for everything, but especially in advanced Redstone devices, this system makes just understanding them and improving them in general a whole lot easier. So, we're going to talk about that in the next video, and in addition, we're also going to talk about how we can actually make faster adders, because clearly, making the cell faster isn't what's helping us. So, thank you, and I'll see you next time.